Alright, so I wanted to talk about one of your UAM equations, and specifically where it comes from. This is one way you can derive it. So let's just say you have an object moving with constant acceleration, right? And I'll use x for position, although it could be in the y direction. This object could be moving in any direction you wish. So now let's say your acceleration, just to make it simple, your acceleration is positive. And I'll make my velocity graph start at some initial velocity that isn't zero, okay? Something like that. And then my position graph, I'll have it start at zero position and speed up. Okay, let's see if these correspond to one another. Yeah, looks like my object sped up. And see here, now I can I'm just going to shorten my graphs a little bit, make it a little easier to see. Not that one too far. Okay. Let's make this smaller. There we go. There we go. That looks nicer. Alright. So, if I take this area, we already talked about that's going to be acceleration times time, and that's going to be my change in velocity, right? And that means that AT is going to be equal to V final minus V initial. And that means that, let's see here, V final is going to be initial velocity plus AT. And you'll notice that that is the equation of this line, right? So now I want to take this area on the velocity graph. And there's essentially two ways I could do it. I think I'm going to take this rectangle right there and add to it this triangle right there. So I'll add those areas. So let's figure them out. So the rectangle, that height on this side is V initial, and then later on we have a final velocity, V final, right? So what I'm looking at is V naught T, that's the rectangle there, plus, let's see here, notice that V final minus V initial is AT. So this amount here is acceleration times time, right? So AT is the height of the triangle that you see, right? This height here is AT, yeah. I have to divide by 2, but I also have to multiply by the base of that triangle, right? So I get AT times t divided by 2, okay? And of course, the velocity and acceleration are vectors, and the triangle and the rectangle, since those are the areas of a velocity graph, that's going to be displacement, right? So, almost there. Now we're talking about, let me rearrange it, make it look nice. We're talking about displacement being equal to initial velocity times time, plus 1/2 AT squared. It's looking a lot more like one of the UAM equations on your reference sheet. Now if I just put final position minus initial position in place of my displacement, or change in position, right, I can rewrite everything here. So what I'm looking at in the end, when all is said and done, is my final position has to equal my initial position plus my initial velocity times time plus 1/2 AT squared. So this is a vector equation, and you'll notice that this equation is a quadratic, represents the graph on my position graph, and this equation here is the equation of this line on my velocity graph. So I'm really just showing you how the areas of the acceleration graph tells you the velocity graph, and the area of the velocity graph tells you the position graph. Okay? So that actually gets you, what is it? Equations 1 and 2 on your reference sheet. Those are the UAM equations. And notice that these equations assume a constant acceleration. So you can only use these equations when the acceleration is constant. And this term here, constant acceleration. So making your motion maps and really verifying that you have a situation of constant acceleration is critical. Okay? The other critical thing about these equations is they're not just regular old equations that you put numbers in. Every quantity that is a vector has a direction to it. And so you have to be very conscientious about making those vectors in the correct direction. If the acceleration and velocity are along the same axis, then you can use plus and minus. But if accelerations and velocities are not along the same axis, you're not going to be able to just use plus and minus. Okay? I hope that helps, and thanks for watching.